Welcome back to the session 3 of the module 2. In the last previous class, I think you have come across the numerical problems. Mainly we have dealt with respect to the usage of the hydraulic formulas, okay, Manning's coefficient. We also come across the Cutter's equations and the formulas which we have dealt with respect to the usage of the Hazen-Williams equations also. Now, normally in India, we go for designing the sewerage system by using the Manning's formula, which is suitable for our tropical country. In this regard, let us continue the numerical problems. In this part of this class, I am going to solve some of the numerical problems. Remaining similar problems will be dealt or it will be given to you as an assignment. You need to complete it. Later onwards, we shall move for the factors affecting variations of the velocity and what are the hydraulic formula in the half running full conditions. So, we shall also go for deriving some of the formulas which have been earlier utilized for the designing of the sievers. Let us get to know one by one. Now, let us take upon the problems related to the circular siever running half full condition. Now, take down the problem. Calculate, or what we call it as a design a siever running half for population 50,000, assume n is equal to 0.015 and s is equal to 0.0001. Once again I repeat, design a siever for half running, or we call it as running half for a population 50,000, assume n is equal to 0.015 and s is equal to 0.0001. Now, when you go for analyzing the problem, first let us get to know what is the data which is problem number 2. Okay, given data, first one they have given the population. Population they have given as 50,000. Next, we also come across for the population which is given with respect to the scale of 50,000. The next, another important thing it is, they have given n is equal to 0.015, okay, the rugosity coefficient, and slope is equal to 0.0001. Observe it in a careful manner. Population n and only 3 data are being given. How to solve the equation? This kind of the problems only insisting for calculation of dry weather flow. Okay, dry weather flow condition, not the wet weather flow condition. If it is in the case of wet weather flow, you need to go for utilizing rational formula for calculating the stormwater drainage, okay, or the discharge condition. Let us get to know population. They have not given what is the per capita to assume it. So, therefore, we need to make some sort of an assumptions while going for it. What are those kind of an assumptions? Population, you need to estimate what is the rate of the wastewater that is being discharged. Okay, based upon the wastewater discharge, you are going to find out the dry weather flow condition. If you know the discharge, the next thing it is, given condition it is the half running full condition. Please make a note of it, half running full condition. Therefore, the area or what you have taken as pi d square by 4. But instead of that, what you come across, you go for using the hydraulic mean depth where r is equal to, that is a by p, giving rise to d by 4. That condition is being suitable for this. Now, let us make an assumption. So, make it as a step 1, determine dry weather flow. Determine dry weather flow. In order to determine the dry weather flow, therefore, you need to utilize the population. So, population we cannot only utilize it, we need to estimate based upon the per capita as well as even with related to the usage of the peak factors also to be considered for it. So, let us get to know by using all those consideration. In this regard, we need to make certain assumptions. assume the following conditions. What are those following conditions? Let us get to know. First one is rate of water supply is equal to 150 to 180 liters per capita per day. First set of an assumption. Next, second one, you have assume peak factor is equal to, remember this, we have also come across to deal with respect to in the case of the water supply and treatment engineering also, peak factor is equal to 1.8, okay, and then next thing it is we need to determine the water is being converted in terms of an 80% of wastewater, okay. Assume the water is converted in terms of 80% of wastewater. 80% of the wastewater. Now, when you have come across for determining all these assumptions, the next step is you need to determine what is the value of the Q. So, in order to determine the value of the Q, now what we have to calculate first the average daily demand and then maximum daily demand. So, therefore, first one we need to calculate the maximum daily demand by utilizing these two datas. Finally, we need to go for conversion of the water to wastewater, okay. So, then therefore, maximum daily demand of water is equal to peak factor into the average daily demand. What is that? Let us get to know in this. So, therefore, maximum daily demand of the water, the bracket I have written it, that is equal to peak factor is 1.8, average daily demand is equal to population into per capita demand. So, when you have taken population into per capita, 1.8 into population is equal to 50,000 per capita is, let us take it as 180 LPCD, okay, let us take it as 180 LPCD. So, let us get to know the calculation part. So, 1.8 into 50,000 into 180, okay, how much for this time? Go for calculating it. Here you are going to get the value and you need to convert in terms of an liters, in terms of an meter cube per second, because discharge will be always represented in terms of that. So, therefore, divided by 24, converting in terms of in 60 minutes and then 60 seconds. Okay, this is a one criteria. So, you will be going to get the terms of the maximum daily demand is equal to this much in terms of a meter cube per second. Now, next thing it is, the hint it is, I am going to give you. So, what is the dry weather flow? So, therefore, dry weather flow is equal to 0.8 times of the maximum daily demand. That means, whatever the water that has been utilized, 80% will be converted in terms of an wastewater, okay. That will be giving you dry weather flow. So, therefore, whatever the values that we have obtained, so if we multiply by 0.8, so therefore, you are going to get the values in terms of an meter cube per second. Okay, let us calculate for this. Meanwhile, you people also calculate it. So, here if I am going to come across 1000, so now you are going to get it as 0.1875 meter cube per second. Okay, now 0.8 into 1 point, that is 0.1875 meter cube per second you will be going to get an answer as 0.8 into that. So therefore 0.15 meter cube per second. This is the first step where we have determined the dry weather flow condition. Next, moving on to the next calculation, what they have told, circular siever. So the geometry of the siever with respect to which condition? Half full condition. So whenever it has been running in the half full conditions, normally you need to utilize the continuity equation. Know that step 2, determine the diameter and velocity of the pipe. Of the circular siever. Circular siever. Now, what is the next step that you are going to come across is, so you know that Q is equal to A into V, where here it is in a half full condition, and area, how you need to determine it. So in this regard, we have to utilize the formula, especially the velocity. I need to determine it. If I need to determine the velocity, is being given by 1 by n r to the power of 2 by 3 and then s to the power of 1 by 2. We have the formula, r is nothing but the d by 4, r is equal to d by 4, it is a half full running condition. So therefore it is 1 divided by, now given here n is also given, s is also given. When n and s, so obviously we can determine easily what is the formula for this. In turn we can able to determine what is the diameter. Let us get to know here. So 1 divided by 0.015 and r is nothing but d by 4. I don't know what is the diameter. D by 4 whole raised to the power of 2 by 3 and s is equal to how much it is? 0.000, that is 0.0001 to the power of 1 by 2. So this is the velocity. Getting clear with respect to this step? Okay. Now I wanted to know what is the area also. So therefore, in order to determine nature, when it is semicircular in nature, let me take back to this step. So therefore I think this part is being completely covered. Okay. Now by utilizing this data, let us get to go for the complete set of the calculation. Okay. Now we have Q is equal to AV. What is that Q is equal to? So therefore it is given as 0.15 is equal to area is equal to, let me take it as area is equal to half of the full circle. So therefore half of pi d squared by 4. Now we have the equation, call it as 2 and this you are going to call it as 1, this you are going to call it as a star equation. Now substitute 1 and 2 in star, substitute 1 and 2 in star. So let us get to know. So therefore Q is equal to what? 1.15 is equal to, so therefore pi d square divided by 8, okay, into what they have given, 1 divided by 0.015 into d, I can remove the bracket here, okay. So therefore d to the power of 2 by 3 and the 4 whole raised to the power of 2 by 3. Okay, 4 to the power of 2 by 3 into what is given, slope is equal to 0.0001. I'll retain all these things because it has to be clear for you people. Okay, now we have d square and d cube by 3. Everything has been known. Only thing is you need to find out what is the diameter of this. In order to determine the diameter, let us go for the simplification of all these terms and all, and therefore let us make what is the total diameter. So therefore d square and d to the power of 2 by 3. So therefore application of the exponential law, a to the power of n, a to the power of n, and n is a fraction in nature. So therefore a to the power of m plus n. Therefore d that is 2 plus 2 divided by 3, 3 to the 6 plus 2, 8 by 3. Okay, so in this part you go for getting d to the power of 8 by 3. Remaining term, let us get to calculate how it is. Okay, so therefore 0.0001 to the power of 1 by 2 okay, so 0.0001 and divided by you have 4 to the power of 0.66 and then you have divided by 0.015 okay, and multiply by pi also. So therefore you have 0.104 and here you have 0.15, that is equal to d to the power of, everything has been computed here, 8 and everything. Okay, let us get to know what is the value. If you go for checking is, now therefore we have d to the power of 8 by 3 is equal to 0.15 divided by 0.104. Okay, so therefore 0.14, let me take the inverse of it, 0.1048, it will be, take it as 0.105, I will be going to take it, okay, 0.105 will be going to take it. Next thing we have is related to, so 0.15 divided by 0.105, 1.42, therefore d to the power of 8 by 3 is equal to 1.428, which implies that d is equal to 1.428 whole raised to the power of 3 by 8. Okay. How much you will be going to getting it? It is d is equal to 1.14 meters. Okay. Sometimes there may be changes how we are going to take the factors and all, 1.14 or sometimes you will be going to get 1.15 also, depending upon how much decimal places it has to be carried out. So based upon that you will be going to get the variations. Now when you have find out the d value, is it not I can able to find out what is the value of the a also as well as what is the velocity also? Same thing, simple as what we have taken up. So therefore area is equal to half of pi d square by 4. Let us determine what is the area and velocity. So therefore area is equal to half, that is pi d square by 8 we have taken. So therefore that is equal to pi by, what is the value of the d is equal to 1.143. So 1.143 the whole square. How much you will be going to get it? So let us go for calculate 3 meter square. So therefore area is equal to 0.513 meter square. Then what about the velocity? So therefore velocity is nothing but q divided by a, same thing. So q is equal to what? What is the discharge that we have taken? It is nothing but equal to 0.15 meter cube per second. So therefore 0.15 meter cube per second divided by 0.513 meter square. So therefore you are going to get the velocity in terms of a meter per second. This is the formula that we need to calculate it. So therefore let us compute it, the formula. Okay, so 0.292 meter per second. Normally you may get even the terms of 0.30 or something. Okay, so this is the conditions where you go for allocating what data which is being given to you. I hope so this set of the problem is being clear with you people. So this is the final formula for getting out what is the area as well as the velocity and the diameter. Okay. So there will be certain changes with respect to the decimal places. Similar set of the problems will also be given. See, whenever the problems are being given, you need to have certain criteria as in assumptions to be kept in the mind. Then only it will be suitable for you. Otherwise, you will be remaining blank and you cannot know how to write it. These are all the certain conditions which you need to remember it. Okay. So perhaps I think you have come across the problems in a neat manner. Now, without wasting much part of the time, let us go for next set of the formula. You can also determine even by using this set of equations also, same thing. You will be going to get the same value. So only thing it is, whatever you have taken, you go for cross checking it for the velocity v. Okay, fine. Now, I hope so you have determined the set of the parameters. Now, let us move on for the next set of the topic. Now, let us go for taking the formulas related to the self-cleansing velocity. Once again, I am going to repeat the minimum velocity of the flow required for the passage or maybe the conveyance of the wastewater or maybe the storm water, anything which contains some sort of the solids where it will not tend to deposit. That minimum velocity which is being required to pave off all those particles or carry out all those particles in the siever system, that velocity we call it as a self-cleansing velocity. Next, non-scoring velocity means the maximum velocity at which the particles does not tend to score or maybe creating the abrasion on the surface of the material, that is the inside or the surface portion of the material, that we call it as a non-scoring type of the velocity. Therefore, with related to the self-cleansing velocity, we have some hydraulic formula may be determined with respect to the some of the geotechnical terminologies. So therefore, what is that? Let us get to know. So the self-cleansing velocity is being given by Vs is equal to, we have the formula. Okay, the Vs is equal to square root of 8k divided by f into SS minus S divided here common and into G into D. So SS minus S, that is, what are those terminologies? Let us get to know. Where Vs is the self-cleansing velocity, self-cleansing velocity. So F is the Darcy's frictional factor, and what is the K? Characteristics of the solids. Characteristics of solids, which is giving the value of, I think, 0.0044. Next, what is S? S is mainly related to the specific gravity of the material or the solids, because it tends to settle at. So therefore, specific gravity of the solid particles. Solid particles. And what is the S is specific gravity of the sewage. Specific gravity of the sewage. You don't have any sort of a derivation, only the part of application is being there for your problems. So specific gravity of the sewage, or what we call it as a wastewater. Specific gravity of the solid particles we have in the range of 2.65. The next thing that we come across is mainly related to the G. G represents the acceleration due to gravity. Acceleration due to gravity. And then you have D. D is nothing but what is the diameter? Diameter of what? Diameter of the solid particles. Not the diameter of the siever. That is different from this. Okay. So diameter of the solid particles. And in other sense also, Vs is also being given by another formula, we have 1 by n, 1 by n. So therefore, you have the square root of k into d divided by, we have f into ss minus s divided by s, where n is called as a rigorosity coefficient. Rigorosity coefficient. Rigorosity coefficient is mainly related to the theoretical area to that of an actual area. That kind we call it as a rigorosity coefficient. Normally it is being also referred as a frictional coefficient. Frictional coefficient. That is the one thing. R is hydraulic mean depth. So these are the set of the formulas, and we also have a limiting velocity for this particular sort of the constants. Okay. Now major thing it is in this particular aspect, let us get to know what are the effect of the variations of the siever. Okay, while designing we need to have some of the features, that is effect of the variation of the sievers. The effect of the variation means flow has been in a variation, it is non-uniform in nature, so therefore sometimes there will be a full flow condition, or maybe running half to 2/3 full condition, or maybe running in extreme low conditions. So therefore low flow, no moderate flow as well as full flow conditions. These are the effect of the variations related to the sievers designing aspect. So how it mainly depends upon, it also depends upon the diameter or maybe the particles which are being present there. Normally whatever the particles which are being arising from each and every houses, they will be having in terms of an mm, not in terms of in meters, in terms of an mm only, the particles, mainly the fecal matters and whatever the things. If you are going to take in the case of an stormwater drainage, whatever the pebbles or any other things, they will also in turn get carried away. I am not telling that in the case of the residential. There are some cases where in the sort of a residential activities, or maybe in a newly built type of the houses, or any of the grit materials will tend to flow along with respect to the normal wastewater flow in the siever systems. So they are taking this into the consideration. We need to check what is the variations. Obviously variations you have come across in the module number 1 itself only. What is the rate of the flow or the effect of the variations of the wastewater generations. Similarly, based upon that itself only, we have to consider the peak factor for it. Sometimes there will be a low discharge during the peak hours, or what we are going to call it as from 9 to maybe 2 o'clock, or maybe like from 10 to 3. Afterwards again what happens? The rate of the flow will be tend to increase at during the evening as well as during the morning time. Routine purpose. Okay, this is one of the things that we need to take into the consideration. That is the one extrinsic factors. Intrinsic factors means here for the hydraulic design, what are the particles that are being entering, and in the designing aspect, what are the special, whether maybe in terms of an laying of the gradient that we call it as a slope condition, okay, type of the siever material that is utilized, okay, and in a final condition related to this, we also come across maybe the self-cleansing velocity. Self-cleansing velocity. The minimum velocity as well as the maximum velocity, we call it as non-scoring velocity. Non-scoring velocity. Okay. So these are the factors being responsible for the designing aspect. Okay, this is the intrinsic factors. Remember it. Okay, so whatever the designing features that you come across, normally let us go for the listing out of the points or the consideration related to the designing feature. So what are those design features? As I have told, First one is mainly related to the formation of the zones. Whenever you need to construct a siever systems, formation of the zones is very important. Whether the topography, it has been laying in a flat area or maybe a hilly area, or maybe there is a larger depression or an elevation. That is one of the considerations, the area lying where the siever system or the network has to be provided under the flow of the gravity condition. Next thing, it is arrangement of the siever lines. Arrangement of siever lines. This arrangement of the siever lines, as I have told, based upon the zones, it has to be provided always from the higher level to the lower level conditions. That is the one thing. Next, third one we have, it is related to the quantity of the sewage, or what we call it as a quantity of the wastewater And one more thing, arrangement of the siever lines. Sometimes what happens during the outfall or any other things, higher elevation, if you wanted to create or construct the wastewater treatment plant, therefore pumping system has to be adopted for it. Or maybe at the lower elevation itself only, a large depression has been made where the outfall has been created in such a manner that whatever the sewage which has been carried and it has been flowing at the bottom like a well we have, and that will be pumped into the wastewater treatment plant and sent to the equalization basin. Quantity of the wastewater, as I told, based on the effect of the variations, the quantity of the wastewater may be at the morning, evening, as well as the in holiday times also the wastewater tends to change. Next, another condition that we have is the velocity of the flow. So based upon the velocity of flow, whether the minimum velocity or the maximum velocity, it has to be in an optimal condition. Next, fifth one, which kind of the sections that you're going to create? Section of siever. Okay, whether it may be you're going to give you the section of the siever, it is mainly related to the continuity equation, and the slope is to be taken into the consideration. So these are the utmost designing features that we have come across in the designing of the sievers in a hydraulic manner. So what are the zones, how the arrangement has to be done. There is also an skill work labor is necessary. You cannot go for an haphazard arrangement. It has to be a complete arrangement. Quantity of the wastewater that is being generated is also a critical factor. Now recently we have solved the problems, how much amount of the water is being generated, and velocity of the flow, it has to be in an optimal condition. It should be neither less than the scoring, that is we call it as a self-cleansing velocity, nor greater than the scoring velocity. It has to be in the range of 0.45 to maybe in the case of 0.8 or 0.9 meter per second. Next is section of the sievers. Normally it will be always circular in nature because of its economical as well as easy for the design and carrying out the project work. So therefore with this I will be going to end the class, and in the next part of the class we will go for deriving some of the hydraulic formulas. Till then, stay tuned and remember all those concepts. Let me come back in the next part of the class. Thank you one and all.